Okay, so the the variation of this volume factor for saturated oil as you lower the pressure in the system, what happens to the oil, right? Yeah. It loses, what happens when you go through a bubble point, right? Gas comes out of solution, you create a bubble. And what's in the bubble mainly is methane, ethane, okay, the light components. So you're losing gas from the oil, okay? The oil is being degassed as you lower the pressure, okay? The oil is losing its ability to keep gas in solution. Okay? Just like CO2 and water. If your Faris, your carbonated water, if the bottle was not at 2 bar, whatever it's at, and when you buy it, it's got some pressure in it, that CO2 dissolves into it. If you had a bottle that could take 10 bar, you could put more CO2 in solution in the water. Okay, it's the same deal. Okay, if you got a bottle with 10 bar water and CO2, and it's got CO2 on the top, gas, and it's got water saturated with CO2, and you take off the top of the bottle, pressure goes to 1 atmosphere. Obviously, you're going to lose CO2 coming out of the out of the water. Okay, it's the same deal. And if you're a drilling engineer who doesn't really have to know the details of how this really works, you at least need to know that. Okay, because gas comes out of solution from the oil, that's dangerous for you. Okay? Because of gas kick. Now, the simplest way to look at it is that I gave you the initial value at initial bubble point pressure, about 300 bar. We have the BO of 2. That's what I said. It might be 1.5, it might be 2.2, so whatever it is, I tell you that. The simplest thing you can do is just draw a straight line from that point down to the intercept of 1 and 0. 0 gas in solution, we're down to an oil that's not changing at all because there's no gas in solution. Okay? It's not quite that simple, but it's approaching 1. It might be 1.04 or 1.05 because of the temperature difference between reservoir temperature and 60 degrees Fahrenheit. But let's forget that. Let's just say that it's going to be a linear trend kind of going down. That's the simplest way to think of it. In reality, the way it's going to actually look, put that in green, is that there's going to be some departure below that line, like that. And it might be a little bit of departure, and then it's going to kind of, well, what actually happens down here is, I'm not going to get too much into, it's not that much interest what's going on down at the very low pressures, because it has to end up being here because of the temperature difference between the reservoir and 60 degrees. It has to end up here. But then somewhere down here, there's no more gas coming out of solutions, so there's no more shrinkage, okay, basically. So you kind of get something that moves into that. But let's not worry about that. The departure from the straight line, it'll always be below that, okay? So that's the first thing. The second thing, so this is always going to be kind of below. Okay? So that's always going to be the case, 1. 2, the more the departure from the straight line, the kind of oil we start giving it a name. Okay? all these. Okay, if it's kind of linear, along close to the straight line, we call it a black oil. Okay? If it starts departing a lot, dropping below it a lot, we call it a volatile oil. Okay, it's just a name. Don't worry about it. But the volatile oil says that as you drop below the bubble point, you get quite a bit of gas coming out of solution. Every bar you drop. Okay? More so than on the line here. And if you get more gas coming out of solution, what's going to happen? The oil is going to shrink more. Okay? So this, basically, this line is telling you kind of how the oil shrinks. Okay? Just because of the pressure in the reservoir changing. So the larger the deviation below the straight line or the linear trend, it becomes more and more of a volatile oil. So it basically transitions from, we call this a more volatile oil. Less volatile oil, more volatile oil, okay? So the larger the deviation, the more the volatile is the oil. Okay. That means gas coming out of solution faster. For every bar below the bubble point, you get more gas out of solution than if you follow the linear trend. So you get more shrinkage. So the first thing is that we're getting, this downward trend altogether in the BO versus pressure is due to gas coming out of solution. Okay? That's why it's dropping. The more dramatically it drops, it means the more gas is coming out of solution per bar. And we call that a volatile oil. The oil is volatile. What does volatile mean? It means it's ready to explode. Things go up. So it's going towards the gas. So the oil components are moving more quickly to the gas. So that's why we call it a volatile oil. We get more of that oil turning into part of the gas. And the oil shrinks more rapidly. That's not good news in general, because we like oil. Okay? And the oil mobility in the reservoir drops more quickly because it has lower oil saturation. So basically that is the faster gas comes out of solution. Okay? Per bar pressure drop. Okay. The third thing that you should make note of is that because there's this, well, it ends up that the volume shrinkage is kind of directly proportional with how much gas comes out of solution. Oddly enough, okay? So RS is simply a measure of, if we take the oil here at 150 bar, we bring the system from 300 bar to 150 bar, and now we've got an oil here at 150 bar, it's saturated. We take that oil to the surface, and we get a volume factor that's not 1.5. 1.5 would be in the middle, right? If we go from 300, we go halfway in pressure. It's not 1.5. This shrinkage is down to 1.4, 1.45. So it ends up that the the gas in solution, instead of being 100 cubic meters per cubic meter, if it was coming out linearly, okay, if you went from 200, you reduce the pressure by half, you get 100 cubic meters still in solution, okay? But if it's volatile, you've gotten more out, so it's only 100, it's only 80 cubic meters per cubic meter. We take that oil, we bring it to the surface, we only get 80 cubic meters of surface gas. Okay, so this is 80 instead of 100. Okay. Well, it ends up that the shape of the RS curve, the shape, is identical to the shape of the BO. Okay, that's just a general. So the shape of BO pressure is basically, it's not exactly, but it is going to be so close to the same as the shape of this. Okay? It's the same shape. So if the BO drops down like this green curve, then the RS curve is going to follow just the same kind of shape. Okay? And what that results in is that you get a very nice kind of general diagnostic, is that if you plot RS versus BO, it's going to be a straight line. Okay? That's going to be a straight line. I guarantee you. That's your initial RSI. That was your initial BO at the initial bubble point. We can call that RS at the original bubble point. That was 2 and 200. And that's going to go down towards 1 and towards 0. It's not going to be exactly that straight line, but it is going to be a straight line. No matter how volatile the oil is, no matter how volatile it is. Some of these oils are wild, okay? This goes from 2 to 1, but I can show you fields in the world that look like this. This is equal to 3, okay? And this thing looks like that. I call that wildly not linear, okay? It's very, very nonlinear. But if you show me that curve, I can tell you exactly what the RS is going to look like. If you just tell me the one number here, that the RS here is 3,500, or no, your units would be 700 cubic meters per cubic meter, RS there. I can draw the line. It's going to go from basically down 1, 0 to whatever that point is up there. So they're going to look, the RS and the BO are going to look exactly alike in shape. They're always going to end up down here around 0 and 1 approximately, and they're always going to start up here whatever they start at. Okay? So that's the third thing, that's general. Yeah.
Is the plot here assuming reservoir temperature or
Any temperature. Any temperature. The slope will be different at different temperatures. The slope will be different, but at different temperatures, but that's it. Okay. So again, these are the characteristics of a saturated oil property: saturated BO and saturated RS. Okay, RS is the remaining gas in solution. Okay, that's RS in the oil at a given pressure and temperature. That's what RS is. It's how much gas, how much CO2 is left in the water. You know, if you crack open the bottle, it's 10 bars initially, and you lower the pressure to 5 bar, close the top of the jar, shake it up, it's at 5 bar now. Whatever the amount of CO2 left in solution in the water. That's what we're talking about. It's the amount of gas left in solution in the oil. Okay. That's the RS. BO is reflecting basically the shrinkage of the oil because gas is going out of solution. It's losing mass. It's losing these light components because gas is coming out of solution. That's why this is changing. But that's shrinkage in the reservoir, or it's shrinkage at the temperature, because our table is at a given temperature, right? As the pressure drops. So it's the shrinkage at this temperature for our table of the oil. It's the shrinkage of the oil because gas is coming out of solution as the pressure drops. That's what the BO reflects. Okay, so now let's just try to think through, what do you think the oil viscosity is going to do? I said it was 0.2 centipoise for this example, which is very low. That's the oil. If we bring it from 300 bar to 100 bar, what happens? Gas comes out of solution. Viscosity doesn't matter. Viscosity doesn't care what the volume is. Okay, it's a property that is independent of the amount of material, right? Okay, the fact that the oil is shrunken, it doesn't matter to the viscosity. Okay, but the viscosity, do you think intuitively that the viscosity will be higher or lower with less gas in solution? Huh?
Higher.
Because these light components make the viscosity go down. Okay? The less methane you have in your mixture, the higher the viscosity. So that's what's going on. So this thing is going to go kind of like this. I'm going to draw it from in the reservoir. You'll see this slight increase kind of like that. And then as you get to the lower pressures and you get basically no gas in solution, it'll approach this, what we call dead oil viscosity. There's no more gas in solution. Okay? And that's our dead oil viscosity. So it has kind of this shape. In general. So this is the oil viscosity, and it's basically increasing because the gas is coming out of solution. Okay? And for reasons I can't really explain, even though you've got a lot of gas coming out of solution, the oil viscosity doesn't jump up real high. Okay, it just doesn't. It generally is kind of flat, gradually increasing, and it really takes off at the lower pressures. That's generally the case. So I can't explain why. It's a little too complicated. But this is what it should look like. Okay.
Does it have any relation with formation volume factor?
I think it has, if you're going to correlate it with anything, it probably would be oil density. And I think oil density has a little bit the same shape as this, but not quite as severe. Okay, so let's go back. And so what Curtis said is that the three oil properties is viscosity, BO, and RS. That's all you have in your table. And the first question you should ask is say, well, I'm an engineer, excuse me. They didn't teach me anything in the first 2 years at university, not in high school. Nowhere did they ever talk about BO. Well, they talked about BO in the United States, body odor, but that's not what we're talking about. Okay? They never talked about BO, and they never talked about RS. So what's the deal here? I'm an engineer to do calculations. What did the guy with the apple and gravity? Newton. Okay? Gravity. You need to calculate the effect of gravity on flow. You need mass density, right? Mass density. Where's my mass density? It's not here. It's not in my table. Okay, we've got our viscosity. That's fine. We've got our description of composition. That's the RS. It's kind of like how much of each component. But we don't have the density. So what we need to talk about before we break here today, we have to talk about how do we get oil density. Okay. From RS and BO. Viscosity is not going to help us, okay? Okay, this guy here will give us that and that, right? At least the ratio of the two. And the BO gives us oil volume at the pressure and temperature of interest divided by this guy. Okay? Mass density is the mass of the oil over the volume of the oil. The mass of the oil, where does it come from? It comes from the mass of the gas in solution in the oil plus the mass of the component oil in the oil phase. So it's the mass of the two components divided by that. Okay. Agreed? No tricks. Okay, it's just standard stuff. So the question is, how do we get these two guys from this? Okay, that's that we have to figure out. Now to do that, we have to choose arbitrarily some basis, okay? What we're going to say is that we've got this volume of oil. We take it to the surface. We get this here, and we get this here. Okay? So let's just say, for the sake of argument, that I have 1 standard cubic meter of this. Okay? This is an arbitrary choice. It's what we call a basis for the calculation. I could have chosen 1,000 standard cubic meters of that. I could have chosen 328, or any number I like. Or I could have said, well, I've got 1 cubic meter of the initial volume. I could do that. I mean, I can pick anything arbitrarily. But I'm just going to say I've got 1 of these. So if I've got 1 of these, then we can start doing something. Okay? So the mass of the oil component from the oil is just the volume of that times what? Times the density of that component at standard conditions. This is at standard conditions. That means this has to be at standard conditions. So I'm going to have to give you the mass density of that oil component coming from the oil for you to do this calculation. Okay? The mass of the surface gas coming from the reservoir oil is the volume of that surface gas coming from the oil times the density of that surface gas coming from the oil. Again, these are all at standard conditions. So what's the volume of gas for our arbitrary choice? Well, the volume of gas, because RS is defined as that over that, right? RS. And we know RS. That's one of our tables. So this is equal to the volume of oil from oil times RS times this density. Okay, this we know. So now from the equation, we can write this equation as mass of the gas from the oil. So that's volume of oil from oil times RS times the gas density plus volume of oil from oil times the density of oil from oil over VO.
Can't we change VO to formation volume factor times?
Not yet. We're just doing the algebra. Okay? So we don't lose any steps along the way. So we've got the mass of the surface oil component, the mass of the surface gas component. We put those two masses together, and what is BO? That's defined as the oil volume over this, right? Well, this thing up here that can just be rewritten as divide top and bottom by VO. That's okay. So then we get RS plus, that cancels here, all right? But this term here is nothing more than BO. And that's the equation for oil density in terms of RS and BO. We didn't even, in fact, we didn't even need to have this arbitrary choice of the but that means our black oil PVT table or formulation or whatever requires the specification of this and this. Okay, we have to know that surface oil density of gas and oil. These are needed. But they're constant. That's a constant, and that's a constant. Okay. So implicitly, if we know the BO and the RS, we can calculate the oil density. But we have to know the surface densities of the component gas and the component oil. Okay? So those have to be specified. And this is the equation. Now, in Chapter 7, it talks about the fact that that density is not really physically constant. Okay, it actually does change. In other words, if we take our original mixture up here that we had from if we go down to from the initial pressure of 300 bar down to 150 bar, if we bring that from down to 150 and 50 and whatever pressure it is, what you'll find is that the new oil that's created, if you take that to the surface, it doesn't give the same surface oil and surface gas. It's a different, in reality, it's got different amounts of benzene and propane and all these real components, so that in reality, the surface oil being derived here, as you flash the oils at different pressures, it's not a constant. This surface oil is not just surface oil. Its density actually changes. But in the black oil PVT formulation, it's a constant. Okay, you ignore the variation. Okay? You just have to ignore the variation. In reality, this is a function of pressure, as is this. It's ignored. This is ignored. And instead, we just use some constant value. Okay? So this kind of takes care of the oil, the discussion of the oil phase and the oil PVT properties, which are saturated. We haven't talked about the undersaturated yet, okay? So let's do that, and we'll close oil. We'll kind of close oil today, and then Thursday we'll start talking about the gas phase. So far we've talked about saturated, oil phase, BO, RS, and we also talked about how that varies, right? We talked about the fact that BO and RS vary kind of linearly, maybe non-linearly with pressure, okay? But in the same shape. So they end up that BO and RS are proportional with each other. Oil viscosity is kind of, it's increasing a little bit as gas comes out of solution, but then it really takes off at low pressures when all the gas is gone. But now we're going to talk about undersaturated. Oil phase. Okay. And for the reservoir I started talking about, which was a gas cap with an oil, all right? It's hard to see when in the world am I going to see an undersaturated oil? Okay? You might ask that question. We go back up here. You say, well, Curtis, you know, this is a gas, this is saturated. It's saturated at the gas oil contact, right? Because that gas and the oil are in equilibrium. Okay. But what happens is that even in this reservoir here, even if the composition of oil is constant with depth, which it might be, the pressure versus depth is going to look like this. Through the gas zone, it's going to be kind of more or less straight. The density of gas is not very much, maybe. I'm just going to make this in red. This is the pressure in the gas. It's increasing a little bit. And then you hit the oil, flip over to oil, and then the pressure in the oil increases with proportional to density, according to Newton, you know, density, static column of liquid. And then we get down to the water, and then the pressure increases even faster, according to the density of water, right? Looks something like that. Now, I'm going to plot in a dashed line, the bubble point pressure. Okay? The bubble point pressure is at the contact right there. Okay? The reservoir pressure equals the bubble point pressure because it's in contact with the gas. But if we say that the composition with depth, there's no variation, it just remains the same, then this goes like that. Okay? So now the bubble point variation with the depth looks like that. The reservoir pressure looks like that. So if we look at the bottom of the reservoir down here, the reservoir pressure is 20 bar higher than the bubble point pressure. Okay? That's undersaturated. It's undersaturated by 20 bar. The pressure here in the reservoir is greater than the bubble point pressure. That is the definition of it being undersaturated. If the local pressure is greater than the oil's bubble point, then it's undersaturated. So at the bottom of this reservoir, where we turn into water, okay, right there, that oil at the bottom is undersaturated. In fact, all of the oils are undersaturated except at the contact. Okay. So now I want to know, what are the properties of this oil down here at the bottom? That's not in my table. In my saturated table, the highest pressure I have in that table is the initial bubble point. That's the pressure right here. There is no BO at the initial pressure, at the water contact. And if you can't give that number to your model, you can't calculate initial oil in place, and you get fired. Okay, because you have to calculate the initial oil in place. You have to do basic calculations. I want the density of the oil down at the bottom, for example, to calculate how much water will cone up into the oil reservoir when I start producing. I need to know the oil density of that oil down at the bottom. So I need to know the black oil PVT properties under saturated conditions. So to get the undersaturated oil phase properties, the first thing you need to know what is the oil bubble point, or what is the oil RS value. Either one. That's fine. We need to know that. Okay. The next thing is that at all pressures greater than that bubble point, the composition of the oil remains the same. Okay, it's undersaturated. It's constant composition. But if you've got an oil and the pressure at the GOC is 4,000 psi, and at the bottom of at the water oil contact, I said it was 20 bar, so it's 300 bar at the gas oil contact. It's 320 bar at the water contact. That's 20 bars above. Okay. It's the same composition of oil at the water oil contact and the gas oil contact. Same composition, same oil, just at a higher pressure. What happens? Let's say that we take 1 kilogram of oil from the GOC, 300 bar, and we go to the laboratory and we say, take that oil to 320 bar. What's going to happen to the volume? Okay. So that the mass of that oil is going to be the same, basically undersaturated as saturated. Okay, the mass is the same. We just take the mass down to a higher pressure, but the oil volume at the undersaturated condition is going to be less. You're compressing it, right? Okay. If we take either of these oils to the surface, how much surface oil do we get? The same amount. Okay? You get the same mass. You take the same mass through the same process, same composition, you get the same amount of surface oil. Okay? Surface oil in the undersaturated state is equal to the surface oil in the saturated state. It's just whatever it is. So what's going to happen is that the BO undersaturated, which is the undersaturated oil volume over this here, saturated oil volume over the same surface oil volume. If this was 2, this is going to put equal to. Not equal to. This is going to be the volume of the undersaturated oil gets smaller. We're compressing it. So this is going to have to be bigger. So this is going to go to 1.9x. Or 1.8 or something. Something less than 2. Okay. So basically I'm just going to sketch somewhere up here, this one here. Here we're at 2. That means that if we go to a higher pressure, this BO, it's going to look something like that. This is the undersaturated. For that initial oil, with that initial composition RSV. It's got that initial composition 200 cubic feet because the GOR remains constant here. We're just compressing the oil. But the oil volume is decreasing as we increase the pressure. I've exaggerated it a little bit here, okay? But it's basically being compressed, okay? So on the undersaturated side, the shrinkage of the oil is not really shrinkage, it's compression, okay? So this is a compressibility effect. Okay, we have to quit. They're going to get upset with us.